Hello everyone, I am Dr. Savitha M and I will be discussing some topics on engineering chemistry under VTU 18 syllabus. The first topic I shall be discussing is on module 1 electrochemistry and energy storage system. Okay, all these videos I will be uploading in the channel My Intuition, which is given down. Please do subscribe for this for other many other videos, coming videos also. So first topic I shall be discussing is on the electrochemistry, where I will be discussing more focus will be given on the electrochemical cells. Okay, so now electrochemical cell, as you know, electrochemistry is a branch of chemistry where we deal where which deals with the interaction of matter with electricity. And in this chapter we will be discussing more on electrochemical cell. And as you know, electrochemical cell is a device which converts chemical energy into electrical energy and vice versa. Okay, and accordingly it is classified as galvanic cell, which is a device which converts chemical energy into electrical energy, and the vice versa, that is electrical energy to chemical energy, the device which converts is called as an electrolytic cell. Okay, so now to understand this we need to know various thermodynamic functions to understand how the cell works and how to construct a cell, all these things. Okay, so the potential of a cell, or the ability of a cell, will depends upon four fundamental functions. The first one is internal energy, enthalpy, Helmholtz free energy, Gibbs free energy. Okay, these are the potential energy which is defined as the capacity to do work of a cell. Okay, so first coming to internal energy. Now the internal energy is the energy possessed by a system, and the change in the internal energy can be expressed in terms of heat. That means change in the heat. Okay, the second one is enthalpy. Enthalpy is dependent on the internal energy and the pressure and volume of the system. The internal energy of a system varies, that is the heat changes will be done when there is a variation in the pressure and the volume. Okay, and the third one is a Gibbs free energy change, which is denoted by G, and the change is denoted by delta G. Okay, so the Gibbs free energy change is given by the relationship between the enthalpy and the temperature and entropy. And next is the Helmholtz free energy. Helmholtz free energy says that the internal energy of a system decreases as the temperature and the entropy varies. Okay, and then we have the entropy. Entropy, as you know, it is a degree of disorderness or randomness in a system, and this entropy depends upon the as temperature also. That is, as the temperature increases, the entropy also increases. And the second law of thermodynamics says that the entropy always increases with the time. Okay, so the it is also the unavailable energy of the system. Next is cell potential. The potential of the cell, that is the capacity of a cell, is designed. Is said the is depending on the electrodes taken. As you know, electrode means any metal when it is connected in a cell, they are referred to as electrodes. As you know, a cell contains two electrodes. One is anode, another one is cathode. The anode is a negative electrode and the cathode is a positive electrode. Okay, so now the when the anode and the cathode, that means the electrodes are dipped in their own metal ions, that is which is referred to as electrolyte, and they are connected externally through the voltmeter. And similarly internally again, these, since these are in the solution state, they will be taken in different containers, and they have to be connected internally through a salt bridge. Okay, so when the the connections are, or the circuit is complete, you can see that the anode undergoes oxidation and the cathode undergoes reduction. Okay, taking the example of Daniell cell. Daniell cell, as you know, contains zinc as anode and copper as cathode. The entire reactions you have studied in your PU classes. I am just referring to that to explain the cell reactions. Okay, so the zinc is dipped in an electrolyte and the copper is dipped in its own electrolyte, that is copper sulfate, and both are connected through a salt bridge. Okay, so now the reaction is the electrons flow from anode to cathode. Okay, so the direction of the electrons is from anode to cathode. Okay, the electrons move from anode to cathode, and what happens is the reactions, how the, where are the electrons generated, how are the, what reaction leads to the generation of electron is, see at the anode, zinc undergoes reaction oxidation to give electrons. Okay, the zinc ions are formed and electrons are also released. The electrons enter the external circuit and come to the cathode compartment, whereas the zinc ions dissolve into the solution. Okay, you can see there is a small dissolution, there is a small part of zinc has been converted into zinc ions, and zinc ions is dissolved in the solution, and the electron enter the external circuit and go to the cathode compartment. And at the cathode you can see the copper ions from the solution, that is you have taken the electrolyte as copper sulfate. Copper sulfate has copper ions, Cu2 plus ions. These ions go near the cathode, accept the electrons which has come from the anode compartment and get deposited. You can see some deposition is there of copper. Okay, so that is, it is accepting electrons. That means the anode compartment there is a tendency to lose electron oxidation, and at the cathode compartment the metal ions accept electron, that is reduction takes place. Okay, so this ability, that means whether the metal prefers to liberate electrons or accept electrons depends upon the potential of that electron, and by convention IUPAC has referred to this potential as reduction potential. Yes, reduction potential in general means it is an ability of the metal to undergo reduction. Okay, so if the metal prefers to undergo reduction, it will be having a higher reduction potential. Where there are certain metals which does not undergo reduction very fast, then we tell it as it has low reduction potential. Okay, all this we can be getting the idea from the electrochemical series. Now, cell potential, what is the major basic for the generation of the flow of electrons? And you can see at the anode the metal liberates and metal dissolves or undergoes oxidation, liberating electron. When the electrons are liberated, these electrons stay on the metal surface, and similarly the ions, the positive ions, for example in a Daniell cell zinc undergoes oxidation to give zinc ions and electrons. Now the zinc ions which is liberated into the solution stay on the near in the vicinity of the anode for a certain period. So therefore there will be a formation of a double layer, that is one positive layer of the zinc ions and the negative layer of the ions, negative layer of the electrons. Similarly at the cathode also, the copper sulfate ions, copper sulfate solution provides copper ions which will be on the surface of the cathode waiting for the electrons. Similarly, the counterpart, that is sulfate ions, will be just staying around the cathode. Okay, so there will be again the formation of a double layer, that is positive layer and a negative layer. This electrical double layer is the basic or the is the origin for the what cell potential, generation of cell potential. Okay, wherever there is a difference there develops potential, and in this case also there is a difference, and that potential is referred to as cell potential, and this electrical double layer is referred to as Helmholtz electrical double layer. So the formation of electrical double layer is the main reason for the flow of electrons from the anode to cathode. Okay, so now summing up, the at the anode oxidation takes place, that is the electrons are liberated. At the cathode electrons are accepted, that is reduction takes place, right? So now when the let us generalize. Now we till now we were explaining, we were discussing on Daniell cell. Now let us generalize when where we take some different any metals M1 and M2. Let us assume M1 metal is taken as anode and M2 will metal will be taken as cathode. See, metal M1 is in contact with its own ions, that is M1 N plus. That means N electrons are liberated. Similarly, if you see the reactions, that is as you know, at the anode oxidation takes place, that is dissolution takes place. The metal dissolves. The metal M1, we have taken it as anode, and it dissolves or undergoes oxidation to give N electrons, and these N electrons enter the external circuit and goes to the cathode compartment, whereas the ions dissolve into the solution. Okay, so how do we represent the anode half cell? Okay, now anode half cell is the reaction of, or is the conversion of metal M1 to metal Mn plus, that is to the form of ions. Okay, so metal is in the solid state and M1 N plus is in the ionic state. Therefore, there is a phase difference which is denoted by a slash. Okay, so this is the anode representation. Now, similarly at the cathode also, the metal ions will be present in the solution. These metal ions go near the cathode surface, accept the electron. You can see the reaction above. The metal ions, we are referring to a different metal which is designated as M2. Now M2N plus ions which is present in the electrolyte go near the cathode, accept the electron, whereas the electrons have come from the anode compartment and get reduced to form metal. Okay, this metal get deposited on the cathode. Okay, so now the overall reaction in the cathode compartment or half cell is metal ions M2N plus ions getting converted into M2. Okay, so metal N plus is in the form of ionic state, and M2 is in the metallic state, and they two are different state. So phase difference, phase change is given by a slash. Now if the two half cells are connected by a salt bridge, then the cell representation would be anode double slash by cathode representation. Always in a cell representation, the first part is the anode and the second part is the cathode. Okay, so now since metal ions means it is in the form of the solution, and every solution has a concentration. Here right now, here we can see that metal 1 N plus is in the anode compartment electrolyte, and its concentration is denoted as C1, and similarly M2N plus ions is in the cathode compartment, and its concentration is denoted as C2. Okay, so now this is the cell representation. Okay, now by seeing the cell representation itself, we can come to know what is the reaction taking place at the anode and what is the reaction taking place at the cathode. You can see in the anode the reaction is M1 getting converted into Mn plus, and in the cathode the reaction is M2N plus getting converted into M2. Okay, the double bar denotes that there is a presence of salt bridge. Okay, now reaction at the anode, see M1 getting converted into Mn plus, liberating N electrons. N electrons enter the external circuit and go to the cathode compartment, and M1 N plus goes to the solution. And at the cathode, see the cell representation, it is M2N plus getting converted into M2. See, M2N plus will accept N electrons and get converted into M2. Now what is the overall reaction? Overall reaction is anode reaction plus the cathode reaction. It is also referred to as net cell reaction or the redox reaction or cell reaction. Okay, so the M1 metal plus M2N plus ions, see N electrons will be liberated at the anode and N electrons will be accepted at the cathode, therefore it gets cancelled. Sometimes there will be variation in the number of electrons, therefore in that case we have to balance the electrons, balance the equation and get the number of electrons cancelled. Okay, so the net cell reaction is metal M1 getting converted into Mn plus, similarly M2N plus ions getting converted into M2 or getting deposited as metal M2. Okay, so now summing up all what we have discussed, the cell potential, that is denoted as E cell, E subscript cell, it tells the potential of the cell. It is the measure of potential difference between the two half cells, that is anode and the cathode. We also know that E cell is equal to E cathode minus E anode. Okay, that means the potential difference between cathode and anode is measured as E cell. Okay, so the potential difference is mainly caused, causes, the potential difference causes the flow of electrons from anode to cathode. Okay, so the electrons can move between electrodes because there is a chemical, the chemical reaction is taking place, which is a redox reaction. Okay, and then a redox reaction occurs when a particular substance is oxidized and simultaneously another is reduced. Okay, so during oxidation, the substance or the metal loses electrons and liberating the metal becomes positively charged. Okay, similarly at the reduction, the ions accept the electron and gets reduced, they become negatively charged. If it is already positively charged, it will accept the electron, they go to zero oxidation state. Okay, then the cell potential, the is measured in volts, which allows us to give a specific value of a cell potential. That means if you have a anode and the cathode, specific anode and a cathode, then E cell will be specific value which is fixed. Okay, so now which one will be taken as anode, which one will be taken as cathode, can be identified by referring to the electrochemical series. You have all studied about electrochemical series, and electrochemical series is a series, arrangement of different metals with respect to their reduction potential, and they are found out with reference to standard hydrogen electrode. Okay, you can see all the metals above are having negative electrode potential. That means they have less ability to undergo reduction. Negative charge is there. Similarly, positive charge is there below. It says that they have higher ability to undergo reduction, and all these potential are referred in terms of reduction. Therefore, only reduction potential is referred or listed or arranged, and all these measurements are done at standard temperature and pressure, and therefore they are also they are referred to as standard electrode potential. Okay, now as we summed up, that is free energy, that is energy available to do useful work. That means a system has some energy, and all that energy will not be available to do some to do all useful work. Let us assume if you take a gas in a container which has a piston. Now the useful work is to move the piston out, but we can see that there is also some energy, some will be wasted, which is striking on the walls of the container. That energy is not used up for doing any useful work, because our useful work is pushing the piston out. So the only that much of energy which is available to do useful work is called as free energy. And enthalpy is the change in heat energy of a system. Similarly, entropy is the order of randomness in a system, right? So a randomness or of a system or disorderness of a system increases with the increase in the temperature. That is shown as T delta S. S is the randomness, that is entropy. T is the temperature. The relationship between the free energy is delta H minus T delta S. Okay, so now Nernst equation. Okay, so Nernst equation. Nernst was a scientist who first derived quantitative relationship between the electrode potential and the concentration. We always refer to as anode reaction. We tell anode is, or the electrode is in contact with its own ions. Now, whenever we refer to as ions, that is nothing but the electrolyte. Now, whenever we refer as electrolyte, electrolyte has a concentration. Now, Nernst found out what is the relationship between the electrode potential, the potential of that metal to undergo oxidation or reduction, when there is change in the concentration. Okay, whether the concentration of the solution varies the potential of the electrode. Okay, so that is Nernst equation, and Nernst equation is always derived for a reduction reaction. So considering what general reduction reaction, as you know, reduction reaction is the acception or gaining of electrons. So the metal ions accept the electron and get deposited as metal. That is the reduction reaction. And the reverse of that will be the oxidation reaction. So a um, a redox reaction is written there. Okay, so when there is any work done, the maximum work can be obtained when the delta G, that is the free energy change of a system, is negative. We know that delta G should be negative for a spontaneous reaction. If it is positive, it is a non-spontaneous reaction. So the more and more the delta G is negative, the maximum work can be done by the is done by the system. Okay, so if deriving taking this concept, we can derive the Nernst equation. Okay, so Nernst equation, we know the equation delta G is equal to minus NEF, where N is the number of electrons taking part in the reaction. So previously we have cancelled the number of electrons in a redox reaction. Therefore, after cancelling, what is the value of N, that is the number of electrons, that is considered as the number of electrons. F is Faraday's constant and E is the electrode potential. Now in the Nernst equation, we are now considering only reduction reaction. That means half cell reaction we are writing. That means we are considering only one electrode. So electrode potential, right? So the minus NEF, that means it is a spontaneous reaction. And we have written one reaction. A reduction reaction is metal ions accepting electrons and getting deposited as metal. Uh, this reaction has a free energy change. Now that is free energy change, that is delta G. Similarly, if this reaction takes place at a standard condition, it is referred, the free energy change is referred to as delta G naught. That means delta G naught is the free energy change of the same reaction had the reaction taken place at standard condition, and it is referred to as delta G naught is equal to minus N E naught F. Okay, where E naught is the standard reduction potential, and the standard reduction potential values we get from the electrochemical series. Okay, now uh, we also know that the Van 't Hoff's equation delta G is equal to delta G naught plus RT ln of K, where K is the reaction constant and which is given with by the concentration of the product by reactant. Okay, so we know the substitution for delta G and delta G naught. Substituting that, we have minus NEF is equal to minus NF E naught plus RT ln of K, and dividing throughout by minus NF, we get the equation 5. Okay, now we have it in ln scale. Converting into log 10 base, we need to multiply by 2.303. So we have the equation 6. Okay, so now equation 6, and we also know that if the reaction takes place at a standard temperature and pressure, that is under standard conditions, the value of R will be 8.314 and the value of T will be 298. That is 25 degrees is considered as the standard temperature. Converting into Kelvin scale, it will be 298, and F, Faraday's constant, is 96,500 coulombs. Therefore, substituting all that, that is E is equal to E naught minus 2.303 into 8.314 into 298 divide by N by 96,500, we get 0.0591 divide by N. Okay, log 10 to the base and log K. Okay, so now we have substituting for K means we know it is concentration of product by reactant. Considering the reaction, we have started with the same reduction reaction. In this reaction, we can see that the product is M and the reactant is Mn plus. Okay, so substituting for K, we have concentration of M by concentration of Mn plus. Okay, so concentration of metal is always considered as 1 because it is not in the liquid state, solution state. Only the metal ions is in the solution state. We can specify the concentration of only solutions. We cannot specify the concentration of solids. Therefore, it is all. I mean, it is always 1. Okay, so the concentration of metal is always 1. Therefore, the equation becomes E is equal to E naught minus 2.303 RT by NF log of 1 by metal ion concentration. Just rearranging, taking the denominator into the numerator, we have E is equal to E naught plus 2.303 RT by NF log of metal ion concentration, or at standard temperature it is 0.0591 by N log of metal ion concentration. And if you see the equation, it is clear that, and it shows the relationship between the electrode potential and the metal ion concentration. Okay, so that is the Nernst equation of a single electrode. Now, if you write the Nernst equation for a cell, as you know, the cell has the anode and the cathode reaction. It is a redox reaction, right? So the let us write the anode reaction and the cathode reaction. And finally writing the net cell reaction. Now I am writing the net cell reaction. Now this net cell reaction, considering the same equation what we have considered for Nernst equation derivation of a single electrode, we have E is equal to E naught plus 2.303 RT by NF log of concentration of product by reactant. Okay, now here the product is M1N plus and the reactant is M2N plus. Okay, so substituting that, we have E is equal to E naught minus 2.303 RT by NF log of product by reactant. Okay, so that shows the Nernst equation for a cell. Okay, my next video will be on university question paper questions and solutions for the VTU question papers. Please do watch the videos and also subscribe. Thank you.